Oh, I just knew.
So like this. Okay, great. All right, yeah. Thanks for the invite. I'm very happy to be here because I've been always inspired to like connect more across disciplines. So yeah, this is sort of who I am, what I do. There's more information on my website. I come from self-supervised learning in the visual domain, so learning from data without annotations, which is exactly what large language models are doing. So now naturally, I'm also working on language modeling. And sort of the intersection is, I think, where the most exciting things are happening, where you have these visual language models, which can both understand images and text. And before I start, I just want to give a very, very brief introduction to self-supervised learning, such that we're all on the same page. So we know this rough story about deep learning, this revolution in AI having been made possible by the new algorithms, the hardware, the GPUs, and the data. And I always argue, and nowadays I think also the field is like converging on this point of view, that the most important part is always the data. That's why you don't see OpenAI publishing, or all these tech companies not publishing their data, even if they sometimes publish their models like Mistral or Microsoft, etc. And in computer vision, typically this data has looked like this. In the case of supervised learning, you had the raw images, which are extremely cheap to obtain. But in supervised learning, you always have what we call labels or annotations. So this could be nouns, like, for example, railroad crossing or trogon, which is relatively simple, but even then, sometimes you might need expert knowledge. I wouldn't know what kind of bird this is, but it can go quite detailed, like drawing bounding boxes around it, or even annotating every single pixel. And this can quickly get very expensive. And so in self-supervised learning, the idea is basically, let's get rid of this expensive side. Let's only use the data alone. Let's try to extract some sort of supervisory signal from the raw data alone. And of course, this is also motivated in part by how babies learn, because you're not teaching them, this is a trogon, this is whatever. They probably don't even understand what words you're using yet at the very early stage. So generally speaking, in self-supervised learning, we divide it into two stages. One is the pre-training stage, where we don't use labels. We might use some augmentations, and we have some proxy task, which trains our deep neural network. One example of a proxy task, to make it very simple, is you take an image and you rotate it randomly by a multiple of 90 degrees. And then you have the neural network predict whether it was rotated by 90 degrees, 180, or 270 degrees, or none at all. And so this is very simple. You only need the datum, you apply some sort of transformation, and with that, you can train a neural network. It's not the best self-supervised learning method, but you get the idea. You only need data for this. You don't need human annotations. Once you've done that, you have a really good neural network, which you can then apply to settings which typically have less data. Because the model has now seen all of this large scale data sets, it can typically generalize really well to new domains. So this was a very quick overview of what self-supervised learning is. The question is, why do we want to do self-supervised learning if we have some supervised data sets? The reason number one is scalability. And also we have in the language domain GPT as a proof of concept. So here I'm showing you the scale of 1 billion images. In the middle, you have 1 million. That's the typical size of a supervised data set. For example, ImageNet. And Instagram has, last time I checked, more than 50 billion images. And of course, this is like, this is nothing compared to all the data available. Every satellite takes multiple terabytes of data every minute, or every hour, let's say. And you have all the cameras, you have insane scale of pure raw data. If you could learn from that, you would get really, really good models. If there's anything we know from machine learning, is that more data equals better models. There's other reasons why you might want to do self-supervised learning. For example, if you have if you want to build a car detector, you might need to relabel it at every few years. And because you train a car detector in 1972, it won't be able to detect this car as a BMW in 2012, because things change. And things change not, they're not going to tell you when phones are looking different, cars are looking different, clothes, etc. And you would always have to invest money into relabeling your data set, unless you're trying to detect Lada cars, which are great. They completely stay constant. So, but generally speaking, we don't want to detect Lada cars, I think. I mean, I don't know, maybe someone in the room is. Another reason, the ambiguity of labels. So we're all excited about CLIP and vision language models, but still they learn from data where people put captions on it. So if you have labels, like who gets to define what is a house, and does it even make sense to put all of these images into the same bucket of a house or a boat? And of course, like even data sets that everyone is using have like really problematic captions with lots of biases. And also you typically don't describe a lot of things in the captions. So I care about building, in this research stream, care about building good generalizable visual models. So kind of like the eyes of a baby that can then generalize to new settings really, really quickly. And I don't really want to get all of these biases or all of this stuff into the models if I don't have to. All right, and then I'm going to talk about learning from videos. And learning from videos is especially interesting because obviously a baby isn't just flickering through random images of ImageNet at every second. I think it would probably go crazy, and probably we don't do this kind of experiments in psychology anymore, which is good. Videos also allow you to get physics. I think this is somewhere in the UK where they do this crazy thing. But yeah, so people know this. Have people participated?
No, I'm still alive.
Okay. Great. So you wouldn't get from a single frame that something rolls down because of physics and gravity. You need videos for that. Lastly, if we want to have robots which actually do things and learn in new environments, like embodied AI scenarios, you'll have to go to the video dimension. Plus, at the moment, we have this insane scale where probably more than 90% of internet traffic is just on video data alone. So if you care about learning from data, this is the way to go. And with that, I'm going to present this first research work, which we're presenting at ICLR this year in May in Vienna, where we compare basically learning from one long unlabeled video, so just one video, against this classic data set of ImageNet learning. And if you have questions, just let me know. Before that, one thing that I haven't mentioned in this self-supervised learning thing, for example, with the rotation thing, is nowadays lots of self-supervised learning models rely on augmentations. We're later going to talk a bit more about this, but you're basically applying some sort of transformation to an image. Let's say you're zooming in slightly, and then you're pushing this through the model, and you say, okay, these two views of the same data, they should be the same. This is sort of one of the key principles of current self-supervised learning methods in image self-supervised learning. And this might be okay for videos that are looking like this, right? So you have the first frame. Now we're taking views to be frames. First frame is quite similar to the last frame. Maybe the difference is the car is now in the shade. But in terms of meaning, this is fine. But does it generally make sense? If we have a video like this, where the first frame looks like that, and then you wait a bit, and then you take the last frame, it doesn't make a lot of sense to push these two things to be the same. Yet that's how like lots of people have done self-supervised learning in the video domain, because they've just taken what was present in the image domain to the video domain. So this doesn't make a lot of sense. And yeah, so forcing frames to be invariant is limiting. And the solution is quite obvious, especially if you're actually having vision transformers. If you look at this, at the image level, not very much not the same. But what we do in one of our works, which I'm not going to go into too much detail here, is basically we're going to take the spatial features. So after we push an image, or in this case, frames through a video model, we still have the spatial features. So it's not like we only get one feature per frame out, but we actually get some sort of more coarse feature representation for every pixel out. And with this, we can actually say, okay, some things are equal. So some things, for example, the features we get for this number plate, they should be the same in this frame, and they should be the same in that frame. And likewise, for example, for something in the background. So now we can say, okay, the overall features from the whole frame, they don't need to be the same, but the features for the same objects, they should be the same, which means in the background, we need to be tracking during the course of the video, where does this number plate go? And that we can do using self-supervision. And this paper we build on top of a pre-trained model. So this paper we presented last year in Paris. We call it time tuning because we're tuning a pre-trained model that has only seen images. We're tuning it with temporal information of videos. And this was a very high-level overview because I want to focus mostly on this research question, where we wanted to get rid of this pre-training. So we wanted to not start with an image pre-trained video, but we wanted to start from scratch. So a randomly initialized model, and we only train from a single video from scratch. So now we're going to this thing. And this was sort of the goal that we wanted to do. So now it was talking about like which video should we actually use. First thing is, of course, let's pick the longest video ever, because then we have a lot of content if we're still saying one video. But it should also contain a lot of content, right? If it's just 24-hour video of staring at the wall, probably we're not going to learn a lot. It should also be high resolution, right? And then we're starting to get all of these criteria, but that's starting to sound like curating. And we love self-supervised learning, so we should keep things simple. And then the solution is actually to get out and have a walk. So we pick walking tour videos as our data set. They're extremely easy. They're long. They're high res. They typically go through cities, so there's a lot of content inside them. They're scalable. If you type in walking tour videos on YouTube, you get more than tens of thousands of videos. And also you can simply generate more data by just taking a walk through the park. So that's really great. And also at later stages, it's much closer to what a robot would see. So that's quite interesting. So how do these look like? So for example, this a few frames from one of the 10 videos that we're proposing in this new data set. So the data set consists of 10 walking tour videos, each an hour and a bit long, of 4K videos through different cities. So you can see there's a lot of things happening. People like, yeah, lots of people, of course, in there, but lots of objects, lots of sceneries, different sceneries, smooth transitions. So compared to movies, there's no cuts, of course. And together with this data set, we're also proposing a new self-supervised learning method, which we call DORA, Discover and Track, which according to the first author is similar to the Dora the Explorer cartoon, which I don't know myself, but much like Dora, we're basically walking around and learning from what we're seeing. The high-level idea is basically now the following. So we track multiple objects across time. So this is now somewhat similar to the previous work, but here we're literally relying on the notion of objects, which are grouped together. While in the previous work, it was just about single spatial features. And then we enforce invariance of these features across time. So then we're saying, okay, we track, let's say, the cat that's walking around in from frame 1 to frame n. And then if we track that again, we're going to say these two are equal. So in terms of the loss, in terms of how we train, the motivation is very similar to what I described to you earlier. Again, we sort of rely on vision transformers, where we first turn this whole image into patches and push them through a vision encoder. And then we have this thing that we call multi-object tracker, which I'm going to explain in the next slide. But this multi-object tracker gives us objects masks per frame. So for example, this could be looking like this. And this would mean, for example, the object is located here. And then in the next frame, the same object is located here. And then the last frame here, let's say. And with that, we mask out everything else. So we let the model look at the image again, but with everything masked out. And then we say, okay, these two things should be the same, which is a sort of a crude thing, but very simple to implement. And now the thing is we do this. So we apply the normal distillation laws from Dino, but now we do this for multiple objects. So now we do this for not only the cat, which was walking on the side, but also for the bicyclist, which was on the side, and maybe for a car in the background. But we do all of this without supervision. And this is sort of the magic is inside this multi-object tracker. And this multi-object tracker itself is no individual component. It's just a part of the vision transformer. So it looks like this. So we simply take a vision transformer, which has multiple heads. So each head is basically one computational unit, which can look at all the pixels in the image. And typically these units end up being somewhat redundant. For example, here, like all three heads are looking mostly at the patches. For example, all of them are looking at patch number 3. So patch number 3 could be in the bottom left corner, for example, and patch number n would be in the top left. Let's say you just enumerate all the spatial patches like this. And this wouldn't be very exciting because this means the whole model is mostly looking at one singular object. This would happen naturally if you don't apply our method. What we then say is, okay, we explicitly want the model to focus at different locations. So we apply synchron-Knopf optimal transport on this matrix, which is simply like a soft constraint to force the models, to force the different heads to be looking at different locations. It doesn't do it like, it doesn't force it to do it, but it encourages it, depending on how many iterations you use. And the good thing about this is it works. So we can visualize where the heads are looking by simply taking 3 heads. So these models typically have 6 heads. But we just take 3 and visualize where each one of these is looking with the color red, green, and blue. So now we can see that, for example, this car is being only attended with a single head because it's blue. But everywhere where you have these mixed colors like turquoise or yellow, it means 2 heads are looking at it, because you only get turquoise if you mix blue and green. That's why you have turquoise here. So you have 2 heads looking at the same object, which is not what we want. And if we apply the synchron knob, you can see we end up with only the primary, or the red, green, and blue colors. So each head is looking only at a specific object. And you can see that, for example, the scooter is being nicely tracked across frames. So what we have with this is basically that multi-object tracking emerges quite naturally in a vision transformer without implementing any other architecture or anything like that. So this was sort of one of the main findings that we had, but of course it was a representation learning paper. So what we care about, or what the community mostly cares about, is this model that we've now trained with this particular method, does it work well? And in particular, can we obtain performances that are better than training on images? And the answer is yes. So we were very happy. This was sort of one of the best things that we found out. In particular, we'll first compare against training on other videos. So first we compare using our method or the Dino method, which is sort of one of the state-of-the-art methods in self-supervised learning for images, on a random movie, on Kinetics 400, and some other videos. And we first find that our method generally outperforms Dino on all of these different data sets. Moreover, this walking to a data set that we propose plus our method is a particularly good combination, which makes sense because we developed this method to work well with this, because in walking tours, you have lots of stuff going on. Our method sort of relies on that. There's a lot of stuff going on. And actually, I didn't include all of these metrics here, but actually our final method that we train on all of the 10 videos ends up working better than Dino on pre-trained on ImageNet. So we can finally start to put a coffin into pre-training from ImageNet, because we're finally starting to get better models that are trained on videos that perform better on all other data sets, which is great. And also, like we heard it from earlier speaker, Lecan is also very excited about training from videos. So here's a paper as well, where they train image representations from videos, and DeepMind is also working on this. So this is really starting to take off now. On that note, we're also organizing a tutorial in ECCV this when is it? Well, autumn in Milan, which is learning image representations from videos. So where we're gonna explicitly go through all of these methods. All right, then I'm gonna talk about about this paper, which is I think in particular interesting for this community. So this paper is not self-supervised learning, I should say, but it analyzes sort of what do augmentations do. And augmentations, as I mentioned earlier, in the image domain, you take different views. So this could be different zoom in levels, or you apply some color jitters, etc. And they play an immense role in self-supervised learning at the moment. So this paper tries to analyze this a bit. And I'm going to start sort of with a fairy tale here, because it's an interesting motivation for what we do. The fairy tale sort of goes as follows. A long time ago, there used to be a king that lived in the kingdom of the clouds in a very humble house, like this one. And he realized that slowly his eyesight was getting worse, and he wanted to give all of his wisdom to his only child. So he started with backpropagation, but quickly realized that that's way too difficult, so he could never do that. So instead, he started teaching his child the ImageNet 12 classes, or as of course everyone would start doing, right? So ImageNet 1000 categories, why not? So they started looking around, and when they found a cloud, the king would tell his son, this is the class of the wood rabbit. And he would always do this while remembering how he had learned it with the real images. But of course, his child was born in the sky, so it had never seen real images. And they would continue with all kinds of clouds. Sometimes he would have to get a bit creative, saying, okay, this kind of looks like a toad, but also kind of like a whatever bench, etc. And he would go on and on. And it is said that when after some point, when the child went back to the earth, it was proficient in all of the ImageNet classes, and it went all great, despite having never seen real images. So this is sort of the fairy tale, and we want to test whether this works, right? So the first critical question to ask is, what about the dishwasher class? Surely there's no clouds which look like a dishwasher. All right, so yeah, dishwasher class, very critical, and the Tinker class. The first class in ImageNet. Everyone knows this one if you're in computer vision. So the question is now, how can we test this fairy tale? Can you mute yourself? Okay, I think this works, right? And now okay. All right, all good? All right, cool. So yeah, quite an interactive fairy tale here. So the king is a pre-trained neural network, right? You've trained it, let's say on ImageNet, it can predict all 1,000 categories. The child is, of course, a randomly initialized model. We call it the student. So random initialized weights. And instead of having them live in this random kingdom, we're going to have them live in a single image. Here we're having a quite dense image. And what they're looking at is individual augmentations of the single image. So you can see, you can have all sorts of zoomed in versions. You can rotate the image, etc. So you get quite a bit of diversity out. All good? Okay, great. So that's how we can test it. And before I tell you how we do this, I'm gonna tell you the real motivation, which is typically in computer vision, we say, or even in language probably, we say that all natural images, they lie on somewhat of a lower dimensional manifold, where you have, for example, all the dogs here, the cats there, other kinds of dogs very close being together, etc., etc. And then you would have a single image. I cannot see half of my screen, but you would have a single image being somewhere in the middle, and all of these augmentations being sort of still realistic images being somewhat surrounding this. And this compared to the raw RGB space, right, which has 224 by 224, like a huge amount of dimensionality. The real images are actually much smoother in terms of where they're lying at. So the question is, can we extrapolate from a single image to all of these semantic categories? So whether this can work. And the hypothesis behind why this might work from sort of the computer science point of view is the following. If you have all kinds of images that have 0 to 225 channels for red, green, and blue, so that's to the power of 3 for 224 by 224 sized images, which are tiny. This is a huge, huge space, which is insane to imagine. But this includes all the nonsensical random images. But all the real images, if our hypothesis is true, lies on this sort of way more lower dimensional manifold. So let's say this one. And now if we have a single image that looks like this, it already tells us a lot about how all the other real images look like, right? It's already pointing exactly in the right direction compared to all of these other random images. So what we say is that within the space of all possible images, a single real image and its augmentation provide a quite very informative prior about all the other real images for extrapolation. And so in terms of method, I briefly hinted at it. We're going to take a single image. We're going to take heavy augmentations. So we extract small patches, look like this. And then apply augmentations. So here we're even applying cut mix. And then we're going to push them through the pre-trained teacher, which is going to hallucinate these categories, right? There's no ImageNet category in this image, but it needs to output something. So it's going to say, I think this is 5% goldfish, 2% toilet paper, 0.5% tench, etc. And the student network, having not seen anything, but having also 1,000 output categories, tries to mimic what the teacher is saying. So it's a quite simple training framework. We call it knowledge distillation. Importantly, the student only ever gets to see these sort of noisy fake images from this one image and never see real categories until we test the model in the real world, basically. And the training data you can see is very varied, but also very crazy. So you cannot really make sense of, I don't know, this image being like 26% comic book and 24% sarong, which I don't know what it is. Or this being nail, screw, hook, knot. And we can also do the same for videos. So we can make like fake videos by smoothly interpolating between two locations. And then we can train video models. So we can test stuff on video benchmarks. I'm not going to go too much into details. But for example, in the case of video, it's also pretty crazy that the model then says, this is definitely playing bagpipes. And this is definitely reading a newspaper. This is definitely counting money, I guess, because of the round thing. But yeah, so it's quite crazy training data, I would say. But that doesn't matter too much. Let's go to the results now. So first of all, I'm going to show you results on Cypher 100. Of course, if you train the student model while giving it the Cypher 100 training data, that's going to work best because it's literally the same data. It's kind of like training it supervisedly. If you give it instead Cypher 10 data for the distillation process, that means the student model can look at Cypher 10 data, but then gets tested on Cypher 100. You already get a slight decrease because they have slightly different data distribution. If you only use 20% of Cypher 10, you're already getting quite a bit of decrease. And in the brackets, I've written down how many number of pixels these sort of data sets have. And our single image only has 2.8 million pixels. But despite being only 2.8 million pixels, it actually works better than the 20% of Cypher 10 for the distillation purposes. And in fact, we tested a bunch more images for the Cypher experiment. And here they are ordered from top left to bottom right in terms of how well they work for this purpose. You can see that actually the more complex the image, the better it is for distillation. So it roughly, very roughly, correlates with compression size in JPEG, because JPEG can only compress stuff that's simple. So the more complex the image is, the more actually JPEG requires storage space. So that's why here we have size in megabyte. And this is true for these images. However, if you took a random noise image, random noise doesn't work at all in terms of distillation, but you cannot compress it. So it would be all the way to the right, but at the bottom, basically. And yeah, so we tested a bunch of images here. And now the key metric sort of is, okay, where would we get when we do this on ImageNet, which is sort of the key data set for computer vision. So the teacher model gets 69.8%, and random guessing would be 0.1%. Is there anyone from computer vision that, or like even from other domain, that would like to take a guess where we end up with?
So the question, is
20?
the student the same size of the teacher?
It is, in this case, it's bigger, actually. Student is bigger. Yeah. So I heard 20%, okay. We'll beat that. We actually matched 69%, which is funny because the student model has never seen real images, right? But we can match with this technique, we can actually match basically the teacher's performance, which is really funky. And we can even degrade the learning signal. So it doesn't need to mimic the whole output distribution from the teacher. it can also just get the argmax. So the teacher looks at this image and says it's toilet paper with 0.5, but if 0.5 is the highest among all the other output categories, we then train the student to output toilet paper, for example. And even that works. It doesn't work as well, but for ImageNet, we still get like 40% accuracy on this, which is crazy. Oh, 44%, yeah, compared to 69%. Yeah, audio and video also works. I'm gonna skip that. This is actually quite interesting. So here we use t-SNE, so don't take it too seriously. But what you can see here is that the training patches, they're described with a circle, and all the real images, they're described with an X. And what you can see indeed is that all the training patches, they're quite similar and sort of accumulated in the middle, and all the categories, the real images, are outside. So this is quite exactly like the picture that I've shown you, where we train on this very similar pattern in the middle, and then we can successfully extrapolate to all the other categories outside. And for ImageNet trained models, we can actually visualize what these models think a particular category is looking like. So in this case, at the top line, I take a model which was trained normally using supervision, and at the bottom, the distilled version. And you can see it has quite a good notion of what a harp looks like, even though it has only seen this one image in the city. Similar for butterfly. There was no butterfly in the original image. And panda. So it really knows how a panda looks like, despite never having seen one. Same for lifeboat and other categories. So this was also pretty crazy to me, that it can learn such a good representation from just this single image plus its augmentation, plus of course the supervision signal from the model. And now the question is why, right? So I want to put one hypothesis forward here, which I'm very curious what you think about. So here's our data set. Here's a screenshot from the data set where they put GoPro cameras on top of babies. Exactly when they were developing key visual aspects. You're more the experts. And then you can analyze these data sets. So you can take the gist distance in all of the images. And this is like a very low level metric. But you see, okay, it roughly looks like this. It peaks at like 0.2 roughly, or 2.5. And then we can do the same for our data set. It peaks at whatever, 0.3. And if you compare these two, they're pretty similar. And they're especially way more similar compared to, for example, ImageNet, which peaks at like 0.8 or 0.7. So I guess what this means is our data set is much, much closer to the data set of, or in terms of statistics, to what a toddler is seeing compared to ImageNet. And so maybe this high correlation is actually useful for learning. Hypothesis. I don't have any proof for this. So yeah. And yeah, so these are the teams for the works presented. And yeah, thanks. And I'm happy to take questions.
I have 2 questions.
Just to get an order of magnitude estimate, so how many augmentations do you need for your...
How many we need, I don't know. What we did was we took this image and then we generated a data set which was 1 million size. So then it was the same size as ImageNet, so we could just do the same number of epochs. But I mean, I would imagine after you take 50K augmentations, it's starting to become very redundant. But of course, the space of applying augmentations, different zooming in, rotation, color jitter is exponentially huge. So you won't run out of, every single sample is different.
Yeah. So just in the spirit of linking to how animals or humans do it. So we do a lot of circading, right?
Yeah.
We don't take in a full image at one time. Do you see a link between that and then the sort of cropping and stuff you were doing?
I would say the circading is quite interesting in terms of how we train vision transformers nowadays. So not that similar to the last work, but in both of these works, we use vision transformers, and they can actually, you don't need to input the whole frame. You can actually just input like these patches, let's say, or just a few patches and train the model like this. So then you give it less inputs. It's actually much faster to train. It doesn't work with convolutional neural networks because they would see like a boundary where suddenly you go into black space or something that would create create artifacts, but with vision transformers, you just leave all of these other patches out. So there's something there, I would say, yeah. But in terms of combining, yeah, I don't know. I don't think there's anything that has combined all of these things together. Yeah.
Can I, building on that, do you think maybe that where babies look would be at the bits of the scene that would be more informative? I guess you could quantify sort of the value of looking at different patch plots, how much to learn from different augmentations.
Yeah.
This idea that babies steer towards more informative stuff.
Yeah, that's a good point. We actually have one paper where we take this data set from single image distill and simply apply self-supervised learning methods on top of it. And there we ablated the effect of augmentation. So there we've found, for example, that this random resized crop where we zoom in and slightly change the aspect ratio, that has the biggest effect, for example. And we have one more workshop paper at the moment where we basically generate this data set again, but then try to distill it further. So, or like prune it, that we only keep points in the data set which are informative, and you don't end up with like one of these crops, which is just a single color, because that doesn't tell us much for anything. So yeah, so maybe, but we didn't do the comparison to babies, so that would be interesting. Yeah,
maybe
thanks.
last question before the launch.
Have you looked at the error analysis that the distilled network is making? So for example, are they more general, like two very distinct objects, or can the network distinguish also very ambiguous kind of thing?
Yeah, we did a bit of error analysis. It's very hard once you have 1,000 categories. I couldn't find, I mean, I didn't spend crazy amount of time, but I didn't see any particular patterns. It was doing extremely well on some very strange categories and badly on other categories. And this might change in the course of like running the model again. So I couldn't see any particular patterns there. One interesting thing maybe that I can note, even though it wasn't in the question, but if the teacher model is too good, so if the teacher model was trained with a lot of augmentations, that means actually the teacher model will output always the same thing. So it won't be varying depending on what kind of patch it gives. And then this whole process doesn't work anymore. So if the teacher starts to become invariant to all of these noises, it will always output whatever, junk or something. And then the student model cannot learn anything, which is quite fun. So you need a bad, like not the best teacher in order to be able to do this. So yeah, thanks.
Great. I think if you have more questions, we can talk during the lunch session.
Yes.
Thank you. Thank you again
Thanks.
for the great talk.